Hello everyone. I hope you're enjoying the conference so far. My name is Sumaye and I'm going to talk about this paper. So I have been working on this technique. It is called AMPR. I will explain the terminology. What is it standing for? Um, the outphasing power amplifier was introduced to me by my colleagues Pavel and John. And based on my experience, when I was dealing with the power amplifier, and when I looked at the issue, the problem that is happening, it is called zero crossing. So I came up with this algorithm, and after simulation and evaluating the results, it seems that it is a good idea. So I worked on that technique to come up with this idea. Um, I'm a lecturer at TU Dublin, Technological University Dublin, here in Ireland. Um, the time that is for my presentation is 3:30 in the morning, and I have two small children. I couldn't just make noise at house. I would wake them up. So my apologies for sharing the recorded video with you guys. I hope you guys have fun and looking forward to come to Malaysia, hopefully in the future. Now, let's just get it started. The outphasing system is very popular because it is providing very high efficiency when it comes to amplification stage. So compared to other power amplifier designs, this is also popular because of the impairment, distortion, uh, and the way that you can go around it, to be honest. So I'm going to start explaining how exactly we create that impairment, and we separate the signal at basement, and the design of the power amplifier itself. I have a small block diagram here. You can see that there is this block in the middle, which is called signal component separator, or SCS. So just imagine if I have my basement signal, I am separating it in a way that both signals are carrying the data. In a way, they are separated with equal phase from one another. It is very important to have the separation done in a way that they can be cancelled out at the end. So once I have them separated, they are passed through individual power amplifiers. That's the part that is called outphase power amplifier, because we have two power amplifiers and then they are sharing the job. They are taking a part of a signal, each of them, and after the amplification is done, they are combined back together. So the power combiner block at the end of the block diagram is describing that. The separation is important. I'm going to show in the next slide. Just before I move to the next slide, um, I'm highlighting where exactly the technique is applied. It might be a question of some people where exactly your technique or your algorithm can be applied. So the best place for um, the technique is before the separation. Um, the reason is simply because we want to optimum. We want to make the effect of that optimum. So after test, I realized this is the best place. I actually tried it for individual power amplifiers, and the reason I emphasize on this place for applying the technique is because um, minimum complexity is added to the system. We talk about that a little bit later. Now, if I have the base signal as ST, I don't want to make people feel boring or bored about the mathematics behind it. Just a quick review. I have this arc cosine added and subtracted from the main signal in order to create outphase signals, and that's how it works. So if you look at the link vector diagram, the main signal would be the ST, and after separation we have S1 and S2. So the angle of the signal and this signal, the part that is added and subtracted, they should be equal to one another. The reason is because when they are combined, they should cancel each other and we should end up with that original signal. Now, from the inverse fast Fourier, just the nature of any digital signal, this ST can take any random form. It can have any power level and it can have any angle itself. So when you're looking at this diagram, these vectors can move absolutely anywhere, and there is no way that we can predict that. We can only observe it and measure it. There is no way of knowing when they are having, for example, 90-degree angle, when they are having 180 angle, and so on. We just know that they are taking places randomly. And so, based on this diagram, there is another thing that we can observe, is that the power or absolute of this vector is associated with the level of the power of the signal itself. So later on I'm going to show what do I mean exactly, and when things can go wrong, when the problem is caused. So far we are familiarized with the outphase and how two power amplifiers are sharing the job of amplifying the signal. Now, here I have two vectors. I'm looking at two main scenarios that are very well known when it comes to outphase power amplifier. On the right side, you would know that in some cases, when the signals that are separated from one another, they are actually overlapping one another. And that means that the angle is taking zero value. Because of that, when they are overlapping, because of having the exact same power level, the original signal is going to have raised level of power. As you can see, is really high up to this point. And in this case, it's double the separated signal. This is actually not good. For those of you that are familiar with Cris factor or Cris factor reduction or PAPR reduction, so this is when that case is happening, that story is happening. I am not emphasizing on that. I have some results that I'm publishing in separate papers, but this is also causing the problem for us. The solution for that would be to get some sort of algorithm or technique to minimize that or to avoid that scenario. Now, here in this paper, I'm looking at this particular scenario. When two separated signals have really big angle difference between them. The phase is really large. Here I want it to be visible, but the reality is these two vectors can be same as the blue line here. And that means that they completely cancel each other, and so the combined signal would have very small value. And reality is that that will have zero value, and that is called zero crossing. Why we don't like it? What's the problem with that? So signal can have variety of power levels. Why we don't like that? The problem happens when we are looking at the frequency domain. That zero crossing is causing something called bandwidth expansion. If anyone is working on adjusted channel power ratio, ACPR, or anything that is looking at frequency leakage or bandwidth leakage, this will be as bad as those stories. So we don't want any leakage, any extra harmonics, for obvious reasons. We are not allowed to use other bandwidths, and we don't want any leakage to adjusted channels. So this is causing a problem. What's the solution? Of course, there are filtrations and algorithms that can actually remove that leakage. But the system itself, if there is a way of avoiding or minimizing the probability of this problem, so that would be helpful. Here I test the LTE signal, and the type of the modulation scheme that I use is OFDM. Obviously, that is the one that is for LTE. The length of IFFT that I used was about 2000 something. It is possible to test it with 5G and beyond. The reason is because OFD is still a popular choice for all those signals, and so if you're looking at out-phase power amplifier and we are testing it with 5G signal, we would expect similar results. So when I looked at this, I thought with myself that okay, let's take a look at time domain signal. What's happening in time domain? Based on my background, based on my experience, I looked at the time and I observed very similar characteristic between the AMPR and PAPR. So the definition of PAPR, which is also known as crest factor, is to look at the probability of high peaks from happening. So when we are looking at time domain, you would see that sometimes those random sinusoids are creating very high peaks. Remember the way that I was explaining the vectors? Sometimes they are causing very large magnitudes. In the same manner, in very random behavior, we would see that zero crossing also happening. So I came up with this idea, why not we look at the probability of this happening with the same manner that we would measure the PAPR. So I defined this new terminology, average to minimum power ratio, or AMPR. So I am measuring the average. I'm just calculating, summing them and dividing by the number of the data points that I have. As simple as that. So that would give me the average power. And I'm dividing it with the minimum. So I'm taking portions of the signal and I'm finding the minimum power and I'm dividing by that. So that will give me a logarithmic value, which is very similar manner as PAPR, a dB value. I look at that and I see how often that happens. You can use CCDF or you can use any other probability measurement technique that is looking at how often that dB is given to me. So by looking at that, I realize that okay, now there is a very high chance that I can apply similar techniques that I would apply for high peaks. But this time I'm looking at this region. I'm looking at close to zero region. So what I did was I wrote another algorithm. So I defined a threshold. To be honest, finding that threshold was a bit tricky because you don't want to lose data. You don't want to kind of manipulate the dynamic range of power amplifier. But on the other hand, you want to avoid that zero crossing from happening. So that part was a bit tricky, and it was based on try and error and see how I can get a nice threshold to apply, and it's going to give me a beautiful result. So after that, it was just algorithm that is limiting the signal based on this comparison. So I'm getting absolute of the signal, I'm comparing it with that threshold, and if it is greater than the threshold, I'm just passing the signal through, and if it is less than the threshold, please note here the signs are opposite of what I would normally do for high peaks, but you know, the idea is there. I would send this signal. Again, how did I come up with this? The idea is taken from, you know, what you would see based on clipping based Chris factor reductions, which are very well developed, and you would see even in industrial chips that they're using that in even in ORAN or many 5G technologies. You would see that clipping based Chris factor reduction is there. So the idea is coming from the fundamental behind that, but with slight change. So what I'm saying here is that I'm kind of avoiding that critical region, which is around zero power. So did it work? Yes, it did, and I was really happy. So this is the IQ in phase and quadrature result, and as you can see, um, after that limiter or the algorithm uh, is applied, I am avoiding the uh, the zero region, and that made me happy. Um, there is a way that you can kind of optimum that, and there is a trade-off between the dynamic range, not losing the data, not causing internal distortions, and also having that zero crossing avoided. So this trade-off is a nice thing. There is a potential for future work if you want to look at that and see if there is any way that you can kind of not completely remove that region, but you know, get to the optimum situation that you still have going close to zero but not completely crossing it. So here is the IQ, and I think I have another result here. I looked at the time domain again and I was happy because the signal is coming down and it is nice and curvy, so it doesn't have very sharp clip, uh, which is not desired for any wireless um, communication designer, for obvious reasons. If you have sharp cutting, sharp clipping, you're causing extra distortion, so you don't want that. So it was nice and curvy, and again there is a way to play around with that and make it even better. And one way of doing that is by having multiple iterations and having a very smooth cut instead of very sharp cut. That will bring another challenge up, which is having the I50 and F50, and again another I50 and another F50, because you want to have filtration added after any clipping. Anyway, it was working. It is a good idea, and uh, there are some challenges and some possible future works. I would be happy if anyone wants to collaborate on this project with me in the future. So one thing that is kind of trade-off and challenge is when we are dealing with very high data rate. So nowadays the challenge is all about data rate. So um, looking at how much complexity is added to the system and does it worth implemented in real life applications versus providing and maintaining high data rate and bandwidth, that is a very nice challenge and very good area of research. Integrating it with digital pre-distortion for optimum power efficiency, that is also another area that I personally like to explore. Different signals, how do they behave? That is a nice question to ask when it comes to uh, you know application, power amplifier. The characteristic of power amplifier itself brings lots of challenges, and when you change the signal, that behavior kind of matters. And bit error rate, my paper probably lacks that, and it's a good idea to look at that in the future. Well, something that I really like, probably my student, to do is to look at dynamic performance in other aspects. Is it kept the same or no? Because I'm avoiding zero, but am I losing anything or not? Am I limiting the signal? Am I causing any problem to the performance of my power amplifier or not? So thank you for listening, and feel free to contact me or my colleague John. Um, so and keep eye on the Research Center Connect, SFI Research Center and Advanced CRT for opportunities for collaboration, and we are always interested in international collaboration. Thank you very much. Bye bye.